Hi there. This is the sound of an oboe. And this is the sound of a trumpet. The frequency and volume of these two sounds is the same, and yet you clearly hear a difference. They differ in timbre. Because of this, we can distinguish between these instruments. Now we know how to catch pitch and volume in numbers. They can be described by frequency and amplitude of the sound wave. But how to quantify timbre? This seems very elusive, and yet there is a way. If we plot the sound wave as a function of time for both the oboe and the trumpet, you already clearly see a difference in the shape of the graphs. But shape is still a bit vague. What to do? What helps here is the so-called theory of Fourier analysis. It's named after its inventor, Jean-Baptiste Joseph Fourier, a French mathematician born in the 18th century. The theory roughly states the following. Suppose you have a periodic continuous function of frequency f, then this can be written as sum of sines and cosines with frequencies f, 2f, 3f, etc. The shape of the function determines the precise amplitude of each sine and cosine. How does this work? Well, first we take a sine with the same frequency as the wave and scale the amplitude such that it best fits the wave function. What that means precisely is a bit technical. I will not explain it here. We do the same for the cosine. The sum of the sine and cosine already approximate the wave. To improve the approximation, we add a sine and cosine of double frequency, each with such an amplitude that the sum fits the wave function the best. And then we continue in this way by adding sines and cosines of 3 times the frequency, etc. The more frequencies you take, the better the shape is approximated. And in the limit, you obtain an infinite sum called the Fourier series. When it comes to sound, you need only finitely many terms in practice, since the human ear is insensitive to high frequencies. The only choices you make are the amplitudes. In fact, the shape of the graph is precisely encoded by these amplitudes. This way, we obtain a quantitative description of the shape of the graph. The theory of Fourier analysis is of fundamental importance in acoustics, optics, and signal processing. But its applications are not constrained to analyzing periodic signals. In fact, Fourier himself was not studying sound or light, but rather heat conduction through material. If you have an iron rod and heat it at some point, how does the temperature in each point of the rod change over time? You may be surprised to learn that Fourier could solve this by writing the temperature profile in the rod as a Fourier series. Do you want to know how to find the Fourier series of a given function and how it can unexpectedly help you to solve problems like heat flow? At university, you can learn all about it.